The topic of this lecture is characteristics of broad beams of charged particles. The objectives for this lecture are to describe the underlying physical processes that shape the depth dose distributions for different charged particles, and to describe field size effects. This presentation assumes the audience is familiar with ionization and stopping powers, multiple Coulombic scattering, Bremsstrahlung, and nuclear reactions. This slide provides a short list of general references concerning light ion teletherapy. This slide shows a hierarchy of charged particle interactions. Charged particles can interact via non-elastic or elastic collisions. Non-elastic collisions can occur with orbital electrons, creating Cherenkov radiation, excitation, ionization, or annihilation products. With light ions, there is very little Cherenkov or annihilation. Non-elastic collisions with nuclei can produce Bremsstrahlung or have an intranuclear cascade with subsequent evaporation of nucleons. For light ions having energies in a teletherapy range, however, very little Bremsstrahlung is produced. On the other hand, the intranuclear cascade and evaporation is very important in attenuating the primary ions and producing secondary particles. Elastic collisions with both orbital electrons and nuclei result in scattering, which is important in beam shaping within the radiation head, interacting with heterogeneities within the patient, and modifying the shape of the depth dose distribution. This slide shows depth dose distributions for 6 non-range modulated charged particle beams. 4 of these distributions were measured with an ionization chamber and a water phantom, while 2 of them were simulated with the Monte Carlo program MCNPX. The figure on the upper left is for a 6 MeV electron beam and should be familiar to most people working in radiotherapy. The dose rises slowly with depth to a maximum and then gradually drops. The center figure on the top row is for a 250 MeV proton beam. The dose is relatively constant with depth for most of its penetration, rises rapidly just before the particles lose all their energy, and then drops sharply almost to zero. The figure at the upper right is for a 200 MeV anti-proton beam. This distribution is very similar to a proton beam, except the peak is slightly broader and it has a long tail. The figure at the lower left is for a 218 MeV per nucleon helium ion beam. Its distribution also looks similar to that from a proton beam, except the peak is a little narrower and the distribution has a small tail. The figure in the center at the bottom is for a 290 MeV per nucleon carbon ion beam. The peak is even narrower than the helium beam and the distribution has a larger tail. The figure at the lower right is for a 969 MeV per nucleon iron ion beam. Although this charged particle beam would not be used for treatment, it is useful to show in a comparison because some of the features that are present only at small levels in other beams are more apparent in this beam. The iron ion beam dose distribution has a large tail and both the entrance and tail regions decrease with depth. This table lists the various processes that occur with each beam to give them their characteristic shapes. With each beam, the stopping power increases as the energy of the particle decreases. This increase is small for electron beams, but is the most important process for the other beams. A process that is very important for electron beams, but is not important for any other beams, is the increasing obliquity of the particles with depth, leading to a buildup in fluence and thus dose. Straggling due to stochastic energy losses is a small effect for all the beams. Straggling from multiple scattering paths is very important for electron beams, somewhat important for proton and antiproton beams, and less important for the heavier particles. Straggling due to the particles taking multiple paths through heterogeneities is surprisingly more important clinically for the heavier particles. This non-intuitive statement is because the smaller angle of scatter prevents the dose distribution from being blurred, resulting in localized regions of under and overdose. Bremsstrahlung is only important for electron beams, as the heavier particles are moving too slowly for this effect to occur. Scatter from the radiation head of the light ion beam treatment unit is most important for electron beams because of their light weight. However, it cannot be ignored for the other beams. Nuclear attenuation is not important for electron beams, is slightly important for most of the light ions, is very important for the iron ions because it leads to the descending shape of both the entrance and tail regions of its dose distribution. Buildup from secondary particles occurs in all beams. For electron beams, it is most obvious with a clean, well-collimated or scanned beam. It is difficult to see the effect on the depth dose distribution for proton beams, but it is, in fact, there. It is much more important for carbon and iron beams as both target fragmentation and projectile fragmentation occur in addition to delta ray production. Lastly, the tail from secondary particles is unimportant for electron and proton beams, is bothersome for helium and carbon beams, and very important for antiproton and iron ions. With antiprotons, this tail is not from fragmentation, but rather from annihilation products, and is directed not only in the depth direction, but also to the sides. This blurring of the dose distribution may reduce the beneficial effects of the high RBE products, as it did during the pion beam trials during the late 1970s and early 1980s. This equation is the Betty-Block formula for electronic energy loss. The main factors are the velocity of the incident ion relative to the speed of light, written as beta, and the charge of the incident ion, written as a lowercase z. There are also a series of correction terms that are put together in the term L. This figure plots the electronic mass stopping power of various charged particles as a function of the remaining range of the particle. Notice that the stopping power increases with decreasing range for all particles except for the lightweight electron. Physicists and physicians working in radiotherapy should remember that electrons lose energy at a rate of about 2 MeV per centimeter. A rule of thumb can be formulated by knowing that the stopping power for the highest energy proton beam used clinically, that is 250 MeV, where the range equals 38 centimeters of water, is double that of the electron, in other words, 4 MeV per centimeter. The reason for an increase in stopping power with decreasing range is the speed of the particle. As a particle loses energy, its speed decreases and it has more time to interact with the molecules it is passing, thereby transferring more energy. The reason that the stopping power of electrons does not change much with remaining range is that most of the energy of a fast electron is not in its speed, but rather in its relativistic mass. For protons and heavier ions, most of the ion energy is due to the speed of the ions. This table gives the initial energy, speed, and stopping power for electrons, protons, and carbon ions as a function of their range in water. Note that both the speed and the stopping power of the electrons do not change much with energy in a therapeutic range, while both change dramatically for ions. This figure shows the relative average energy deposition along the track of a single proton that started with initial energy of 155 MeV. The dose distribution was calculated simply by dividing the depth into many thin slabs and calculating the dose deposited in each slab by multiplying the linear stopping power for the energy of the proton entering the slab by the thickness of the slab. If one were to look at a table of proton stopping powers, the maximum stopping power of a proton at the depth of the peak would be 185 times that of a proton entering the surface. On this plot, however, the peak to entrance dose ratio is only 29 to 1 because the energy deposition tallies were done in slabs a 1/10 millimeter thick in the depth direction. This slab thickness is larger than the range of a proton with the highest stopping power, and thus the average energy deposition in a slab is lower than the maximum energy deposition possible for a proton. A measured depth dose curve yields an even smaller peak to entrance dose ratio of only about 4 to 1. Clearly, processes other than the change in stopping power contribute to the shape of the depth dose curve. For comparison, this figure shows the same calculation for an electron beam. One will notice that, along the track of a single electron, a peak does exist. The maximum stopping power at the peak of an electron is 27 times that at the surface, but for the size of the voxel used for scoring, the peak to entrance energy deposition on a plot is only about 2.5 to 1. As seen in an earlier slide, the measured electron distribution usually only has a peak-to-entrance ratio of about 1.2 to 1. Again, the change in stopping power cannot be the only process shaping the depth dose curve. One process that leads to a reduction in the peak-to-entrance dose ratio is the straggling from stochastic energy losses. This slide shows that protons, as do other ions, lose kinetic energy primarily in small discrete amounts as they undergo a multitude of interactions, such as atomic ionization and elastic nuclear collisions. Not all protons will have the same number of interactions, nor will each interaction have identical energy transfer characteristics. An initially monoenergetic beam of protons will thus acquire small energy spread after passing through an absorber. This energy straggling process is important if one is calculating a dose distribution from basic principles or writing a Monte Carlo simulation program, but generally does not enter into a clinical physicist's daily life at a light ion treatment facility. One result of these collisions is the production of recoil electrons leading to secondary tracks such as so-called spurs and delta rays. This graph shows the production cross-section versus initial energy for 3 different incident proton projectiles. Since the spectrum is heavily weighted below 20 keV, for which the range of electrons is less than 9 micrometers of water, these secondary electrons are not important due to routine treatment planning except at low-density tissue interfaces. They are also important when performing dosimetry with gas-filled detectors. Another process, one that is considered frequently in a physicist's daily practice, is straggling due to the particles of the beam taking multiple paths as they pass through the patient. This slide shows plots of particle paths as they penetrate water. These paths were calculated with the Monte Carlo program MCNPX. The figure on the left shows the paths for 50 electrons, each starting with an energy of 10 MeV. One sees that the electrons stop at a myriad of different depths. Even though the dose distribution along the path of each electron has a peak, as seen in a previous slide, these peaks are located at different depths. For a given depth, the total dose from all electrons is due to some large energy depositions and some small energy depositions. The figure in the center is for 50 protons each stopping with an energy of 80 MeV. Although some of the protons stop at different locations, most of them tend to stop within 1 centimeter of each other, so that most of the large energy depositions are close to one another, and most of the small energy depositions are close to one another. This coherent stopping produces an easily measurable peak of energy deposition with respect to depth. The figure on the right shows 500 carbon ions, each starting with an energy of 150 MeV per nucleon. Almost all carbon ions follow the same path and stop at the same location. This makes a very coherent energy deposition pattern, resulting in a peak-to-entrance dose ratio for the carbon ion beam that is much closer to the single particle distribution than is seen with either the proton or electron beams. Before deconstructing a proton depth dose distribution, it is useful to review the components of an electron depth dose distribution. This slide shows a depth dose distribution for an electron beam with different regions color-coded. Near the surface, electrons ionize atoms, generating secondary electrons. A buildup of these secondary electrons occurs in the first few millimeters of depth until an equilibrium condition is met. This is shown in the magenta region. In the blue region, the paths of the primary electrons become more tortuous, with many electrons traveling obliquely with respect to their original direction. This results in an increasing fluence, and hence dose, as the depth increases. In clean beams, this section is often concave upwards. The green region represents where electrons have traveled far enough along their paths that they run out of energy and stop. Because each electron has taken a different tortuous path as seen in the previous slide, the small peaks near the end of their paths are located at many different depths, resulting in an overall gradual decrease in dose. Finally, the red region represents dose from contaminating brimstollen produced in the head of the treatment unit and in the shallower layers of the patient. This figure shows why the dose increases with depth for an electron beam. As shown on the right, an initially high energy beam the electrons are mostly traveling forward. As the electrons cross a target, such as an ionization chamber or a DNA molecule, the dose is proportional to the number of tracks crossing the target times the length of each track. As the electrons penetrate the medium, the electrons have multiple scattering events, resulting in many tracks moving at large angles to the initial tracks, and thus more tracks traversing a target of the same size, as seen in the diagram on the left. The fluence, and thus the dose, increases with increasing depth. Another important aspect of electron beam depth dose distributions is the field size effect. For large field sizes, the number of electrons scattered away from the beam axis is compensated by the number of electrons scattered towards the beam axis, and a dose with depth remains high until the electrons lose most of their energy. For a small field size, many electrons are scattered away from the beam axis, but few are scattered towards the beam axis. Since the cumulative number of scattering events increases with depth, the number of electrons near the axis decreases with depth. The competing processes of oblique fluence buildup and electron loss mean that the depth of maximum dose moves closer to the surface as the field size decreases. This graph shows that the proton depth dose distribution, shown in green, is slightly simpler than an electron depth dose distribution. Secondary electrons and delta rays are produced at all depths, but the range of these electrons is quite small. Secondary protons are also produced, and a small buildup region is present near the surface, but is often difficult to see. It is most easily observable with broad, high-energy beams, where low-energy protons scattered off the collimators do not mask the buildup. Beyond the buildup region, there are two competing processes. The most apparent process is the increasing stopping power. The other process is a decrease in number of protons due to nuclear interactions. These nuclear interactions remove primary protons from the beam, but can add neutrons, secondary protons, helium ions, carbon ions, and other particles. The solid blue curve shows the number of primary protons remaining at each depth. Once the protons slow down and reach their peak energy deposition rate, the protons run out of energy and stop. As shown earlier, however, not all protons stop at the same depth, and so the fractional depth dose distribution just beyond the peak is not represented by a vertical line, but instead a line with a steep slope. This slide is a magnified view of the previous graph centered on the peak region. The range of a proton beam is defined as being the depth where half of the protons stop. This does not mean half of the protons that were incident upon the surface, but half of the protons that continue to cause ionization to the terminal depth. The dashed red curve is an extrapolation of the number of initial ions remaining at each depth. In this case of a 100 MeV beam, only about 88% of the protons survived, and the range is defined where 44% of the protons are remaining. The black curve on the graph on the left shows the fractional depth dose at the range of a proton beam for various beam ranges. The value is around 80% for beams of all ranges. The dashed red curve shows the fraction of protons remaining at the range as a function of range. A linear fit to the data would give a 0.8% per centimeter probability of non-elastic nuclear interactions, but most people generalize to 1%. For low proton energies, this proton loss mechanism is relatively unimportant, but for high energies, more than 30% of the protons are lost before they lose all their energy through ionization and stop. The graph on the right of this slide shows similar data for incident carbon ion beams. As with proton beams, the carbon ion range is found at approximately the same depth as 80% depth dose. The number of carbon ions lost during penetration is, however, about 4 times as large. As with electron beams, scattering plays an important role in the depth dose of light ion beams. This graph shows the depth dose distribution of a proton beam for several different narrow field sizes. The peak to entrance ratio is seen to change as a function of field size. Since protons do not scatter nearly as much as electrons, the major effect of scatter is seen in the lateral penumbra regions. For small field sizes, the penumbra from opposite sides of the field begin to overlap. Due to the increasing cumulative scatter with depth, the dose at depth decreases faster than near the surface, thereby reducing the depth dose at depth. Empirical data for different proton energies and field sizes has shown that for proton fields having diameters less than the range of the beam divided by 8, changes in the depth dose distribution occur. Unlike electron beams, the depth of the maximum dose is not seen to change significantly. To summarize, the depth dose distribution shape of broad charged particle beams is primarily due to energy loss through ionization, but secondarily by nuclear attenuation and secondary particles, straggling, and scattering. The field size can have large effects on the depth dose distribution. Bremsstrahlung is only important for electrons.